Hello again, the Math Dog here. In this video I'm going to look at composite translations of linear functions. This will be part one of a two-part video. Part two will feature some practice problems. In this one I'll go through the theory and then some examples. So composite, what I mean is I will combine horizontal and vertical translations of linear functions. So it would be very helpful to first watch my two videos on horizontal and vertical translations of linear functions. You should have a pencil, graph paper, and ruler ready to work the practice in part two of this video. So let's get started here. So if you just want the formula, here it is. F of x equals a times quantity x minus h plus k. So the general form for translating a linear function f of x in a two-dimensional space is this, where a is your slope, h is your horizontal shift. If h is a positive number, then it's a shift right, like x minus 3, h is positive 3. If h is negative, that would be negative, negative makes positive, that's a shift left. So k is your vertical shift. If k is greater than 0, it's up, k less than 0, it's down. So if that's all you're interested in, then if you memorize this, you can get through this. The thing is, a lot of people have no idea why the shifts are as they are, particularly the horizontal, because it's counterintuitive, as I talked about in my horizontal translation video. Because like x plus 3, you would think, well, shouldn't that be a shift right? Well, actually, it's a shift left. So I'm going to actually, this video is for the curious, to see the why these things are as they are, instead of just here's a rule and do it. Okay, so the next couple minutes I'm going to try to illustrate for you the theory behind the composite translations of linear functions. I'm going to start with what I'm going to call the parent linear function f of x equals ax. Technically the parent linear function is just f of x equals x, but I'm going to include the a here, which is the slope, so I can do a little bit more complete explanation. So I'm going to translate some function f, this function here, f being f of x, in this case ax, h units right and k units up. So I'm going to move this function here h units right, and then I'm going to move it k units up. So this old stands for the origin in the little x, little y axis. This is my origin, but I'm going to shift this up to here. Now I'm going to create a new origin, a new set of axes, and I can do that. I'm going to call it capital X, capital Y axes, and then the new axes, this is going to be the point 0, 0. In the old system, since I'm shifting right h, it's going to be h, and going up k vertically, it's going to be hk. So again, here's my original function, f of x equals ax. Slope is a, which means the rate of change here, or the slope, is a divided by 1. This is the identical function here, except it's been shifted. Again, slope is a over 1. This, I'm going to call this function g of x equals a capital X, and I'm also going to call it y equals a times x. So it's the identical function, except it's starting from a different spot. So I'm doing a translation to here. So now I can create a relationship between big Y and little y. So big Y, what I do is I look right here. Let's start with x, not y. So big X, I look here. So to go from the old value of this point, well, in the old coordinate system, to new value, I have to take away h from little x. So big X is little x minus h, because h minus h gives me 0. And then capital Y is going to be little y minus k, because k minus k is 0. So now my function is capital Y equals ax. So I can replace now y, big Y, with little y minus k. I can make that substitution, and I can replace big X with x minus h. So I'm going to write this function a couple ways here. So first of all, let me add k to both sides. So I get y equals a times quantity x minus h plus k. Okay, and remember that's what I had on the previous page. I can also call this g of x, because this is this function now in terms, this function here in terms of the old coordinate system, a times quantity x minus h plus k. Okay, so I can do either of these. But I also notice, remember, let me make some space here. Note that f of x here is defined to be little a times x. But that means then that f of x minus h has to equal a, because here, everywhere there's an x, this is a substitution here, I'm replacing x with the quantity x minus h. So that means, let's take this function right here and apply this. That means I can write g of x as f of x minus h plus k. Alright, let's even go a little further. So we have now several ways of writing this. We have this. We talked about these two things right here. So I've got three ways. Well, there's even another way that I can write this. So this function here expresses g as a function of f. Okay. So the other thing I can do is I could take this function right here and I can expand it out. So I have g of x equals ax, using your distributive property, ax minus ah plus k. But again, notice f of x is ax here, so I could write this as g of x equals f of x minus ah plus k. So that is yet another way we could express this. So you're probably going, this is overkill here. Why are you doing this to me? Well, again, I'm trying to get into the weeds here a bit and show you the why. But I will also say, even in the Common Core on the state tests at the high school level, there are questions where you have to be able to write a function g of x in terms of a function f of x. So there is some value even at the, say, high school sophomore junior level, and it's nice to know these things so you can navigate yourself through some of these questions. And then in the higher level courses, this is going to be very useful. And then also other functions like quadratic functions and cubic functions, these same type of rules apply to those as what we're doing here. So let us continue. So I'm finishing off with the theory here. Now I'm going to composite a linear function in the form f of x equals, I'm using a instead of m, but normally often you see y equals mx plus b. That's called slope-intercept form of the function. So I'm translating a function in slope-intercept form to another location. So I'm going to translate this function f, which is ax plus b, h units right and k units up. So once again, so here I'm technically I'm starting, here's my old origin, I'm creating a new origin right here. So this is, I'm taking the old origin, new origin here, I'm going h units to the right, and I'm going k units up. Okay, but this time my function's not going through the old origin. This is ax plus b, which means a slope of a to 1. Vertical change is a, horizontal change is 1, and it has a y-intercept at b, which is the coordinate 0b. So in my new axes right here, the new axes, this is going to be the new origin 0, 0. In the old coordinate system, this is the point hk, but then up here in the new axes, this is going to be 0 little b again, because it's the exact same distance from the origin as here. These are both, this is b from here to here, this is b from here to here. In the old system, this is going to be 0 plus h, because I've shifted h units this way, and it's going to be b plus k, because this is k here, but I'm going up another b. So this is going to be b plus, the coordinate of this point is 0 plus h, b plus k. Okay, so this again is the function f of x equals ax plus b. This line is going to be, I'm going to call this g of x also. G of x equals a little a times big X plus b, because now we're centering, this is the big X, big Y coordinate system. You could also write this as capital Y equals little ax plus b, because this is the identical function to this, except we've moved it, so we renamed our coordinate system based on this point here instead of this point here. So let us continue. So let's define big X. Well, big X here is again going to be, from here, to go from old to new, I have to take away little h from x. This is going to be little x minus h. Capital Y here is going to be k minus k. To get to 0 from k, I have to take k away from y. So this is going to be little y minus h. Okay, my function here, the general form, is capital Y equals little a times capital X plus b. So now I make substitutions. I know y, big Y is little y. That should be k here, not h. So I have little y minus k equals a times quantity, replace big X with little x minus h, plus b. Okay? So notice that, first of all, we could multiply this out. I'm going to hold off on that just a second. So I'm going to notice that f of x is equal to ax plus b in this problem. So therefore, notice that f of quantity x minus h, everywhere there's an x I replace with x minus h, is going to be a times x minus h plus b. But that's this right here. So this actually, this expression right here is going to be f of x minus h right from right here. So I can make a substitution then. In this, I can say y minus k equals, this is f of x minus h. Okay. So then rearranging here by adding k to both sides, I get y equals f of x minus h, that's not multiplication here, that's function notation, plus k. So that is one way to write this translation, this composite translation. But then I could also call y, I could call it g of x. So here is g of x, one way of writing g of x in terms of f. So we've now created two ways to express this function g or y in terms of f. Alright, but there's other things we can do here. So let's, first of all, let's go back to this right now. So let's just multiply it out here. I have y minus k equals ax minus ah plus b. So rearranging, I have y equals a, actually let's not multiply this out here, this is going to be a, yeah, let's multiply it out. So because I want, notice that f of x equals ax plus b. So let's rearrange this a little more. So I have y, I'm going to add k to both sides, so I have this. But further rearranging, I'm going to rearrange this to be ax plus b, which I'm going to underline, minus ah plus k. Okay, so ax plus b though is f of x, so I could write this as f of x minus ah plus k. So this is yet another way, and we could call this g of x also. This is yet another way to write g in terms of the function f. Alright, let's show one final way here. I'm just going to write this as, taking this and write this as y minus k equals a times quantity x minus h plus b. Add k to both sides, I get y equals a quantity x minus h, a times quantity x minus h plus b plus k. So notice that if you want, you can rearrange this again like this. So notice this is the, right here, this is what we got in the previous page. Right here, g of x or y is a times x minus h plus k. The only difference here is we have now added a b because we didn't start the original function at the origin. We started it b units up from the origin. So here is yet another way to write this, and I could also call this g of x as well. So when you're doing these problems, you don't have to do all these things, and actually once you do memorize the shift, so again, if it's like x minus 3, this would be a shift right. If it's positive k, it's going to be up, negative k is going to be down. I'm just trying to show you the y, which I do think is important, okay? That you understand why you're doing this. You're not just memorizing a bunch of rules and formulas. So now let's do some examples. Okay, example. Graph the function, given the function f of x equals x, translate the function 5 units right and 2 units up, call the new function g of x. So I have created, here's my original coordinate system, and I'm going to call this the old coordinate system, and there the origin is 0, 0. I'm going to create a new coordinate system here where the old is actually now going to be, I'm shifting it 5 units right, so I've done the graphs for you here, 5 units right and 2 units up. So in the old coordinate system, that point there is 5, 2, but in the new coordinate system, that is my new origin, 0, 0. So I'm going to use this relationship here to compare big Y with little y and big X with little x. So this again in the new coordinate system, this is my new origin, okay? And I'm going to have this new line go through this origin. So let's note that from here, I can see that big X, so to get from 5 to 0, I have to subtract 5 from little x to get big X. Okay, because big X is 0 here, so little x, 5 minus 5 gives me 0. Same idea for capital Y. Capital Y has to be little y minus 2. Okay, so we're calling, again, this is f of x, okay, equals x. It's also y equals x. This is y equals capital X, okay, or g of x equals capital X. So we're going to call this g of x also here. This will be f of x. So now we have this relationship y equals x here. Capital Y equals x. So now I make substitutions. So I replace big Y with little y minus 2, replace big X with x minus 5. Okay? So one way of writing this is y, add 2 to both sides, quantity x minus 5 plus 2. Okay? But notice that f of x equals x in this problem. Therefore, f of quantity x minus 5, everywhere there's an x here, I replace with x minus 5, so this is just x minus 5. So we could write y equals f of x minus 5 plus 2, which is also g of x. So here are 2 ways to write this translation in terms of f. Okay, then another way to do it is, move this over here, I write y minus 2 equals x minus 5, but since f of x in this problem is x, I can replace x with f of x, like so. All right, let's show one final way here. I'm just going to write this as, taking this, I'm going to write this as y minus k equals a times quantity x minus h plus b. Add k to both sides, I get y equals a quantity x minus a times quantity x minus h plus b plus k. So notice that if you want, you can rearrange this again like this. So notice this is the, right here, this is what we got in the previous page. Right here, g of x or y is a times x minus h plus k. The only difference here is we have now added a b because we didn't start the original function at the origin. We started it b units up from the origins. So here is yet another way to write this. I could also call this g of x as well. So when you're doing these problems, you don't have to do all these things, and actually once you do memorize the shift, so again, if it's like x minus 3, it's going to be a shift right. If it's positive k, it's going to be up, negative k is going to be down. I'm just trying to show you the why, which I do think is important, okay? That you understand why you're doing this. You're not just memorizing a bunch of rules and formulas. So now let's do some examples. Okay, example. Graph the function, given the function f of x equals x, translate the function 5 units right and 2 units up, call the new function g of x. So I have created, here's my original coordinate system, and I'm going to call this the old coordinate system, and there the origin is 0, 0. I'm going to create a new coordinate system here where the old is actually now going to be, I'm shifting it 5 units right, so I've done the graphs for you here, 5 units right and 2 units up. So in the old coordinate system, that point there is 5, 2, but in the new coordinate system, that is my new origin, 0, 0. So I'm going to use this relationship here to compare big Y with little y and big X with little x. So this again in the new coordinate system, this is my new origin, okay? And I'm going to have this new line go through this origin. So let's note that from here, I can see that big X, so to get from 5 to 0, I have to subtract 5 from little x to get big X. Okay, because big X is 0 here, so little x, 5 minus 5 gives me 0. Same idea for capital Y. Capital Y has to be little y minus 2. Okay, so we're calling, again, this is f of x, okay, equals x. It's also y equals x. This is y equals capital X, okay, or g of x equals capital X. So we're going to call this g of x also here. This will be f of x. So now we have this relationship y equals x here. Capital Y equals x. So now I make substitutions. So I replace big Y with little y minus 2, replace big X with x minus 5. Okay? So one way of writing this is y, add 2 to both sides, quantity x minus 5 plus 2. Okay? But notice that f of x equals x in this problem. Therefore, f of quantity x minus 5, everywhere there's an x here, I replace with x minus 5. So this is just x minus 5. So we could write y equals f of x minus 5 plus 2, which is also g of x. So here are 2 ways to write this translation in terms of f. Okay, then another way to do it is, move this over here, I write y minus 2 equals x minus 5, but since f of x in this problem is x, I can replace x with f of x, like so. Now let's add 2 to both sides. So I get y equals f of x minus 5 plus 2. So y equals f of x minus 3. Could also put this as g of x equals f of x minus 3. So here's two ways to express g of x or y in terms of the function f of x. And finally, we could take this, just our original here, and add 2 to both sides. Which you're going, yeah, why didn't you just do that to begin with? Well, again, I said because sometimes you're going to have to, if you're going to go into higher level math, you're going to have to be able to express a function g of x in terms of f, and I think I mentioned earlier, if not, that you have to, even in the Common Core curriculum in high school, in the sophomore or junior level test, you have problems where you have to be able to express a function g in terms of f. So that is one reason I have undertaken this video. So notice now, so we have this by the way could also be g of x equals x minus 3. So I know I have a ton of ways. You could say, yeah, it's overkill, but I'm just trying to show you. So this probably is the least obvious. So it does say you're shifting the function f here 5 right. So we've done all the work to show that, but 5 right, 2 up. Okay, this shows that it's equivalent to taking the function, the original function, and shifting it 3 down. And then this shows, again, taking the original function and shifting it 3 down. So these are all equivalent. Okay? Now again, if you just had to do this on a test or something, all you have to do now is go 5 right, 2 up, draw a line parallel to this. So yes, this is overkill, but I'm trying to show you the functional relationships in a problem like this. Alright, let's do another example. So given the function f of x equals x plus 4, translate the function 4 units left and 3 units up, call the new function g of x. So again, practically speaking, all I have to do is take some points. This is my original function, f of x equals x plus 4. Notice it's the function f of x shifted 4 units up. There's your y-intercept. We'll mark this on the new function while we're at it. I could just go from, say, this point, 4 units left, 3 units up. I could take another point on the function, go 4 units left, 3 units up, get a couple more points. Just actually need 2, but get a couple more points and draw a line through it. There's your translated function. But I'm trying to show the notation relationships here as well as just simply plotting the function. I've actually already plotted the function for you. So what I'm going to do here is I'm going to call this is the original origin. In the old system, we'll call this 0, 0. That's old. So this is my new origin here. I'm going to put an arrow here. In the old system, this would be -4, 3, because you're going 4 units left, 3 units up. In the new system, I'm calling this 0, 0. This is my new axis, capital X, capital Y. Okay, so my function is f of x equals x plus 4. So the way I'm going to do this is, again, I have a relationship here now. This line is going to be, the way I'm going to define this is going to be capital Y equals capital X plus 4, or g of x equals capital X plus 4. Alright, so now to come up with my relationship between big X, big Y, little y, I use this. So I know that big X, to go from -4 to 0, I have to add 4 to -4. So this is going to be little x plus 4, and capital Y have to go from 3 to 0. So I have to be taken away 3 from little y to get 0. So there's our relationship, and then we have capital Y equals x plus 4. That should be capital X plus 4. Now make some substitutions here. So this is replace big Y with little y minus 3. Replace big X with little x plus 4. So I have that plus 4. I'm going to put parentheses around that because notice that this is equal to f of x here. Let's add 3 to both sides first. But the way I'm going to start out here is, notice that f of x here is equal to x plus 4. Therefore, f of x plus 4 has to equal, I replace x with x plus 4 plus 4. So that's what f of x plus 4 has to be equivalent to. So notice that right here is f of x plus 4, so I can write y equals f of x plus 4 plus 3, or g of x equals f of x plus 4 plus 3. So that's the first way I'm going to show that I could write g of x or y in terms of the function f of x. A second way is taking this, and I have y minus 3 equals quantity x plus 4 plus 4. Well, again, f of x equals x plus 4 in the original problem, so I can replace this with f of x. So I have y minus 3 equals f of x plus 4. Okay, well now I could add 3 to both sides and I get y equals f of x plus 7. Okay, so that is a second way you could write, and this is also g of x. Let's do that while we're at it. G of x and y are interchangeable here. Okay, so this will be little f of x plus 7. Okay, and finally, let's take this and let's just recombine things. So we have y minus 3 equals x plus 8, because you can remove the parentheses, add it together there. Add 3 to both sides. You get y equals x plus 11. Or g of x equals x plus 11. And if you look, you're saying, well, that doesn't look like 11 up from the origin. Well, actually, we're starting from right here. Okay. Actually, we are starting from the origin. My mistake. Notice you count 11, it's off the graph, but there's your y-intercept up there. So that is, in terms of the original origin, that is correct. The new function is y equals x plus 11. Okay, it's also f of x plus 7. So here's f of x, 1, 2, 3, 4, 5, 6, 7 vertical change, so that works. And then, again, probably the hardest one to see is this. Well, that's a shift 4 left, up 3 from here. So 1, 2, from here we go 1, 2, 3, 4, 1, 2, 3. So it also puts us on the graph, and then you could do that with another point. And so all these methods get you the desired results. This is probably, for most of us, is the easiest way to see what it is, the last one. But I'm showing you sometimes you may be asked to write a function g in terms of another function f. Alright, let's do another example. Without a piece of graph paper and ruler, translate the function f of x equals 3x minus 5, 2 units to the left and 8 units up. Call the translated function g of x. So first of all, this time I'm going to do it the way if you have the motion rules or the translation rules memorized. So I could write g of x, the new function. So I'm shifting x 2 units to the left, so that's going to be x plus 2, 3 times quantity x plus 2 minus 5, and I'm shifting 8 units up. So then I could recombine things using the distributive property and combine like terms. I have 3x plus 6 minus 5 plus 8, and that's going to be g of x equals 3x. Then that's 14 minus 5 is 9. So we get g of x is 3x plus 9. So that's the way to do it if you have the rules memorized, which actually you should, so you don't have to go through all what I'm doing. But now I'm going to show you again the why this works. So I'm going to start with my original function. This is my original axes, 0, 0. This is little x, little y, and this is 3x minus 5. So this is the y-intercept, 0, negative 5, and it's going to have a slope of 3 to 1. So this is f of x equals 3x minus 5. Okay, now I'm translating that 2 units to the left and 8 units up. So for sake of space, we'll put it right here. So this is my new axes. This is the old system, and this is going to be the new system. Well, the old system here would be, and this line is going to be identical to the other one. Actually, let's take that back. It should be up, should be down 5 here. So in the new system, that's 0, negative 5. That's the y-intercept, and a slope of 3 to 1. Okay, now in the old coordinate system, this point has to be negative 2, 8. And a new coordinate system, that's 0, 0. Okay, so using this, we can establish the relationship between x and y. So x is going to be, to go from old to new, I have to add 2 to little x to get big X, and then I have to take away 8 from little y to get big Y. So we have this. And this function, in terms of y, big Y, is to be capital Y equals 3 times big X minus 5, or g of x is 3, g of little x is 3 capital X, 3 times capital X minus 5. So now, my relationship here is y equals 3 capital X minus 5. Now make my substitutions. So big Y is little y minus 8, and then big X can be replaced with little x plus 2, and then I have minus 5. Okay, well again, notice that right here, f of x is equal to 3 times little x minus 5. So f of quantity x plus 2 is to be 3 times quantity x plus 2 minus 5, because everywhere there's an x, I'm replaced x plus 2. So this, in fact, is right here is f of x plus 2. So I can replace that. So I have y minus 8 is f of x plus 2 minus 5. So adding 8 to both sides, I get y equals f of x f of x plus 2, negative 5 plus 8 is 3. Or I could write this as g of x is f of x plus 2 plus 3. So I have this now as a way of expressing g in terms of f. Okay. And remember, we had also g of x is 3x plus 9. Let's put that down here so we can see it. Okay, so last thing I'm going to do here is I'm going to express g of x in terms of f in a different way. So I'm going to start with y minus 8 equals 3 quantity x plus 2 minus 5, And this time I'm going to multiply this out on the right, so I get 3x plus 6 minus 5. I'm going to rearrange this to 3x minus 5 plus 6. Okay, so notice that f of x is 3x minus 5, so I can write this as y minus 8. So again, f of x is 3x minus 5, so this is f of x right here. So I could let's do this again. So I could write y minus 8 equals f of x plus 6. Now adding 8 to both sides. We get y equals f of x plus 14, or g of x equals f of x plus 14. Okay, so I've shown here, again, probably to many of you this would be overkill, but I've showed different ways to represent the translated function. First we have g of x equals 3x plus 9, which is probably the most intuitive. We could write it g of x in terms of the function f this way, or we could write g of x in terms of f this way. So there's 3 different ways I've shown that here. So in this last example, write the function g of x in terms of a translation of function f of x. So in this problem, I'm defining, this is not even going to be my origin, this is not my xy axis, this is going to be my little x, little y here. This is how I'm to do this problem. But before I go into this, let's just see if we know our rules, so so you should be able to do this problem without going through the details. I will go through the details in a moment. So one way is I'm shifting f of x 10 units to the left, because this is from 5 to negative 5, that's a distance of 10. So one way of writing this function g of x is f of x plus 10, because as I've been trying to say many times here, this is counterintuitive. You would think that x plus 10 is a shift to the right, but actually it's a shift to the left, and hopefully we've demonstrated that in these series of videos. The other way is I could go up this way, which also is 10 units. So g of x also could be written as f of x plus 10. So this is a horizontal translation here. This is a vertical translation. Gives you the same thing. Now, why does this work? Let's just do this again. So I'm defining this to be my origin. This is not my origin here. This is the old one, and this will be the new one. So in terms of the old coordinate system, this would be the point negative 10, 0. In the new, this is going to be the origin 0, 0. So notice I go from negative 10 to 0 for x. So to get that, I have to let big X equal little x plus 10, because I'm going from negative 10 to 0. I have to add 10. Y stays the same, okay? Doesn't change. So we get, that should be y, not x. Okay, so we get y equals x plus 10. You might be going, well, but actually this is y equals x plus 5. Well, that's right if we were using this as the origin, but we're not. We're using this as the origin, and notice this is in fact x plus 10, y equals x plus 10. We're shifting this function up 10 units. Okay, so that's not the way we really would want to write this, because most people are thinking, well, that's the origin right there, and that's wrong. So it is correct if this is the origin, which is what it is here. But most people see the graph, they're going to say, well, that's the origin, so that's wrong. So we're going to have to change, we're going to change this in terms of f of x and g of x. So I'm going to write g of x equals x plus 10. Okay, now, one thing, notice that f of x is x here. So since f of x is x, that implies that f of x plus 10 is replacing x everywhere with x plus 10 is x plus 10. So we could write this function as g of x equals replacing x plus 10 with f of x plus 10, which is our horizontal translation. We also could have done g of x equals x plus 10, but since f of x equals x, we could write g of x equals f of x plus 10. So this is a verification of what we showed here. So hopefully at this point, the idea is you don't have to go through all these steps. I'm just trying to give the background proof as to why this works. Sorry I was wrong, sort of sorry. One final example. So in this one we're just going to use the rules. So now the training wheels are off. I'm not going to show the reason, I'm just going to do it. So we're going to graph two things here. F of x equals 3 times quantity x minus 2 plus 4. So the parent function here I'm treating as f of x, or let's call it h of x here because I'm using f of x. Parent function is 3x. That's how I'm going to do it. So this is a shift to right, 4 up. So all I do is I go 2 over, 4 up, put a point there, then I know how to graph 3x, the line 3x, y equals 3x, or h of x is 3x. So from here I go over 1, up 3, over 1, up 3. I could go down 3, back 1, because that's a slope of 3. So then I just draw my line through it, and it's going to look like that. Okay, we could continue that. Okay, so then the second one is, we'll call here the parent function k of x. K of x is going to be, I'm going to treat it as negative 1/2 x. So my shift here is 5 left, and 6 down. So in the practice problems next video, that's how I plan to do these. I went through the theory in this section. I'm not going to go through the theory in part 2. I'm just going to do the problems now. So we're going to shift 5 left, 6 down. So I'm starting again from the origin. This is negative 1/2 x, slope of negative 1/2. So I'm going to go 5 left, 6 down, which puts me right there. So now I construct a slope of negative 1/2. So that's going to be back 2, down 1. That's wrong, sorry, it's a negative slope. So it's going to be over 2 down, let's do it this way, over 2, down 1. I could go back 2, up 1, back 2, up 1. I could go over 2, down 1, over 2, down 1 to give a slope of negative 1/2. So then draw my line through there. So again, let's label these. This is g of x equals negative 1/2 quantity x plus 5 minus 6. And this is y equals 3, or h of x, I guess it's f of x is what I called it. This is f of x equals 3 quantity x minus 2 plus 4. And this concludes part 1 of the video. Part 2 will be some practice questions. Hope this was helpful. Thank you very much. Have a good day.